Hello, everyone. I'm Kathy McGew. I work for D-Wave, and it's actually great to follow Carlton some of this talk because he explains some things that I won't have to. So this is sort of the latest news from the benchmarking team at D-Wave, and this is joint work with my colleague Pao Pare, and you can read, here's the table of contents. And basically in this world of quantum supremacy and quantum speed up and quantum advantage and all these quantum superlatives, we thought it'd be a good time to introduce a new metric, quantum utility. And I want to explain this sort of approach we're taking to measuring performance. And what a milestone is, it's sort of a partial, a limited type of quantum utility. And then I'll show you some results. So, and the point really is, in defining this metric, is that we want to try to capture QPU performance as experienced by the practitioner. A lot of these proposed metrics are really meant for scientists to communicate with other scientists about how well the quantum processor matches theoretical expectations. And I think a lot of those publications kind of leave the customers kind of cold. What does it have to do with me? I don't understand what this means. So we're trying to get to that something a little more relevant to the practitioner. And as Carlton said, this being the annealing model of computation is called a declarative model. And instead of writing a program, you reformulate your problem so that it matches the algorithm, that's the heuristic that's already implemented. And so instead of trying to invent a new algorithm, you have to come up with the transformation, basically. And so you take your original problem, you translate it to a QUBO or a logical input, and then there's the physical embedding step, where it matches the connectivity structure of the hardware, and then I can read it better over here, actually. And then you send it to the QPU, and the answer comes back. It has to be unembedded, it has to be untranslated, and then you get your solutions back. And all of these classical steps surrounding the quantum computation add overhead to the cost. And a user who's actually using our quantum system is going to experience these overheads as time delays. And we need to be able to answer the question, is the quantum computation fast enough and powerful enough to pay for the overhead of accessing the quantum system? And so that's what we're trying to get at here. And so our final destination in the long term is a full-scale, broad demonstration of quantum utility accounting for all of the overheads. We're not there yet, so we establish milestones, we're calling them, sort of narrow definitions of quantum utility with respect to certain types of overhead costs that you're going to face. So the first three milestones in this longer path are milestone 0. We'll measure pure anneal time, which is just the quantum part of the calculation. If we measure that time, and we're going to do the same kind of analysis that Carlton is showing you, as solution quality gets better as computation time increases. That's pretty typical for these kinds of heuristics that we're comparing to. We're not so much looking at how much time does it take to reach an optimal solution as we're going to give all the solvers a fixed runtime and say what's the best solution you can come up with in that runtime. So a different approach in a different type of measurement. So there's pure anneal time. Can the quantum solver return solutions faster and better than classical alternatives? Milestone 1 is when it's not just about the anneal time, it's including the overhead of chip access time, which is the programming step to set up the chip for the computation. And then every time you get a solution from an anneal, you have to read it off the chip, and that adds extra time. And then third is what I'm calling an indirect cost of minor embedding. I'll explain what that means. But minor embedding is when you map the problem to the hardware configuration. So in terms of milestone 0, I'm actually going to skip that part because there are plenty of papers in the literature that basically do that. They measure computation time, they measure solution quality. a bunch of different specific metrics and different approaches, but there are a lot of papers that say this, the quantum processors outperforming classical competition as we measured it. I have the citations at the end of the talk, and I believe one of these is Carlton's paper? Is the Pang et al. So Carlton's paper is on the list. So milestone 1, chip access overhead time. This is just a diagram. It's not data at all. It's a cartoon to explain how things work. But you can see solution quality, lower is better on the y-axis, computation time increasing on the x-axis. And different kinds of solvers worked in different ways. And so in teal here is something you might get from a greedy algorithm. It just picks a random solution, runs down until if you're familiar with that solution landscape, local minima, it rolls down until it finds a local minimum, reports the answer, does it again. So you can bang out a lot of solutions pretty quickly. You're more or less getting a statistical sample of all of the local minima that are reachable from random starts, basically. But it's very fast, but you don't necessarily get very good solutions from it. Simulated annealing here in orange has a parameter. You can tell it how much work you want it to perform given your runtime constraints. You can say I want one solution, in my example 100 milliseconds, and you see this long sloping curve. The more work you allow it, the more iterations it can take while exploring that space, it's going to find better and better solutions. But if you say I want 10 samples in the same runtime, then each sample is going to have to do less work on it, and you can see you don't get as good a quality solutions in that scenario, 10 solutions back. And then there's quantum annealing on the bottom. In my diagram, that long horizontal line is programming time. And in the context of things, it's a huge weight. And then the dots there is the quantum annealer banging out solutions. Each actual anneal is about half the width of that dot, and the other half is the readout time of that dot. So the anneals are quite fast. But they're surrounded by these other time costs, and which are a couple orders of magnitude higher than the anneal time. And so we're trying to understand, well, how much of a penalty is that, and how bad does it get? That's what milestone 1 is about. And milestone 2 is about minor embedding. So you can take a general graph, we call it the logic graph of general shape, and you have to map it, in this case, to a Pegasus graph. And the original graph can have arbitrary number of, a node can have an arbitrary number of edges connected to it. When you map it to the restricted degree Pegasus graph, you might have to take one node in the original graph and map it to some number of qubits, all connected by what's called a chain in the Pegasus graph. And they can each have a lower degree, and that's how you get past the degree issue. So in the example here, there's a big black dot. That's an oversized node, and it got mapped to 2 qubits in the Pegasus graph. They have strong couplings to make sure they give you the same solution as much as possible, and then between them, they're connected to the other 3 neighbors, and so forth. So the point is, when I talk about indirect costs, is that the embedded graph has more nodes than the original graph. It's, in this case, almost 40% larger. And we all know that larger problems are harder problems, and so there's a penalty that the quantum processor pays simply from having to solve the larger graph. And the question is, well, how bad is that? How much is it able to overcome that kind of a penalty? So that's what we're looking at with milestone 2, is about the size differential of the graphs. The classical solver can solve the original graph, and the quantum processors solving the bigger graph. I call that an indirect cost because there is an actual cost to computing the minor embedding, and that's for some later milestone. We're not that's the direct cost, and we're only going to consider that size differential in this milestone. So in order to consider these problems, especially for milestone 2, we generated 13 different input classes, all kinds of categories, all kinds of structures to get as much variety as we could. The first 5 in blue there are native problems. They're generated directly on the hardware graph. There's not a logical and a physical version. They're both the same. So, any kind of solver can read that. The ones in teal are generated. They have logical graphs. They have a logical version and a physical version, and they're embedded using our heuristic embedder, minor. And then the bottom 3 are cliques. Those are the most dense graphs there are. They have all-to-all connection. And we use 3 different weighting schemes for those, and they're embedded with the clique embedder. So in terms of the size of the problem performed or solved by under these different schemes, there's a ratio over here. The number of qubits it's actually the full size of the quantum of the Pegasus graph, because the quantum processor just solves the whole graph. Doesn't matter which ones are being used. You can see there's a 32. The larger graphs are 32 times larger than the smaller graphs in that extreme case. And generally, in the embedded cases, on a fixed size graph, you can embed a large sparse graph all the way down to a small dense graph, because you're really trading edges for qubits in a sense, degrees. So we have a whole range of different graph structures that we're looking at here. All right, so that's setting us up for what we're trying to look at. And so more or less, here's in a nutshell how we set up this test. In terms of the inputs, we have 15 different input classes. There are 25 instances in each class. And we pre-screened them for these instant classes. We actually started out with more like 16 or 17 input classes. But before we did anything, we checked that the problem was hard enough that it took more than 20 milliseconds to solve it classically. Because if it takes less than 20 milliseconds, classical is too easy. Classical solving it before the programming time is over. It's a 20 millisecond lower bound, so there's kind of no point. We know the smaller problems have been too small. They've been too small for all the previous machines for us to get past that, so we're at least looking for something that is feasible to test. And for M1, we looked at native problems, or the native inputs, and the post-embedded inputs, and for the second one, we compared the pre-embedding to the post-embedding versions of each input. We compared to 7 classical solvers. 2 of them read only the Pegasus graph, and they are optimized for that the structure, and they're implemented on GPUs. And the other 5 read general graphs. They all run on CPUs except for the last one, which is a version of parallel tempering that was implemented on a GPU. And what we're going to look at is we'll take different sample sizes. We're going to request 1, 10, 100, or 1,000 samples from the solver. And those samples have to be returned within between 0.02 and 1 second, different time slices. So a combination of a particular sample size and time is called a scenario. We applied that scenario to all the solvers, all the inputs, and looked at which one was best, really. It was a rank-based, who gave you the best solutions. And also, you can ask me about this fair test policy. It was important for us with this big variety of inputs to make sure all the solvers got equal treatment in terms of fine-tuning the parameters. And so we developed all the parameters for all of the solvers were either set to default values, or there was auto-tuning performed to set them based on the input. But that counts as part of runtime if you have to auto-tune. And we saw that as more faithful to the user experience. If there's tuning required, then that's time you pay for. So as I said, we used a rank-based analysis, so we didn't go for approximation ratios we measured it, but really we're just looking at best, first one, the second best, third best, and so forth. And so the results, this is the kind of results that we end up with. Here are At the top, you see 4 scenarios for a particular input called NAT1, and these are all at half-second runtimes, and taking 1 sample, 10 samples, 100 samples, and 1,000 samples. And similarly, in the middle is an input called 3D lattice. Andrew King spoke about that the other day. And at the bottom is Sherrington compactor graphs, which I remember hearing a talk about yesterday as well. So these are, they're familiar inputs to be tested. And we looked at, basically we looked for which solver gives you a line that's below all of the others for all of the 25 inputs. And so in the top, you can see that the blue one is the QPU, and it's winning all 4 of those scenarios, right? In the middle, the first case, the QPU and the green one, which is simulated annealing, are kind of duking it out. But as the sample size gets higher, which means there's less time per solution that can be spent, simulated annealing starts to fail and the quantum annealer starts to win. And then in the bottom, these were the smallest problems in cliques. You can see there are a lot of classical solvers sort of duking it out. They're all tying and for getting good results. And the quantum annealer is sort of in the middle of the pack here. All right? The other thing we looked at, there's winners. And it's possible to tie for the win. So in some cases, it's a win or tie is the same as a win. We also looked, if you look on the right side, especially in the upper corner, a lot of the lines are missing. And that's because these solvers couldn't return, for example, 1,000 results within a half a second. That's a half a second divided by 1,000 per result, and simulated annealing, for example, that's just too much to expect. And so it failed. It's reaching its own lower bound in terms of computation time. So classical solvers sometimes failed. We actually, you'll see, only looked at places where scenarios where the QPU you can tell just by arithmetic which ones it's going to succeed at. So those are the two questions we asked. So for milestone 1, you're comparing anneal time, access time to just straight up computation time for the classical solvers. And all of the solvers are reading the same inputs, which means that they are all Pegasus structured inputs, either negative or embedded. And you can see we had 13 inputs, and we counted up how many scenarios, how many of those inputs does the QPU win on? And the answer is nearly all of them. There's a couple places where one of the GPU solvers did better, but they were all very tight in that case. So here's milestone 1, where we're seeing the QPU winning or tying in 99% of the scenarios, and we consider that a demonstration of the milestone with respect to this particular type of performance. Milestone 2, logical inputs. We looked only in cases where there's a logical and a physical version. The logical solvers, the CPU solvers are solving that smaller problem, and the QPU is solving the bigger problem. And you can see fewer successes from the QPU. There was one input where just about all the scenarios the QPU was winning, and a second input in the upper right-hand corner of this graph, which is the shortest run times, the most samples and the smallest time limits, where the QPU did pretty well, and then an even higher up in the right-hand corner, the third input. We did find 3 inputs where the quantum processor was able to win, and they all tend to congregate in these upper right corner, which is short run times. And as it turns out, large N, these are the 3 biggest problems in our embedded set of inputs. So there's something about when time per solution is low, upper right corner, and N is high, the 3 largest inputs, we're seeing places where the quantum processor can win. And also, those places coincide with more likely to see classical solvers failing. These white spaces here were the places we didn't test where you could tell from programming time that the quantum processor couldn't do it, and most of the classical solvers I think the QPU ones could maybe get one of those boxes, but nobody can return solutions in that fast in the tests we ran. So the places where classical fails coincide with the kinds of problems where quantum is succeeding. And that difference, that distinction was really interesting. So it led us to kind of do a deeper dive and try to understand what it is about the scenarios that make this observable, which led us to understand performance in a kind of in terms of two distinct mechanisms. Here on the left, it's yet another time on the log scale on X and relative error on the Y, and lower is better. These are the biggest and the smallest problems in our test. This is native Nat1 problems with 5,000 variables, and down below we have Sherrington-Kirkpatrick graphs with 175 variables. And so it's 20 times smaller. Is that right? Somebody do the math. And I just picked 3 example solvers. The random one is just sending out random solutions. The greedy one is random sliding down, random sliding down. And then simulated annealing, you can give it a longer and longer anneal time, and you can see it gets better and better. But on the native problem, you can see the QPU is below all of them. The first 3 sort of form a Pareto front of less time, better solution, or more time, better solution, and the quantum processor is just outperforming them all. Whereas on the smaller graph, you can see that greedy is, even though it's stopping in local solutions, by the high end of this process, around 1 second, it's finding putative optimal. We're guessing that it's probably optimal because both greedy and simulated annealing are agreeing that this seems to be the lowest energy they can find. These problems are kind of so big that it's hard to just run an exact solver that could guarantee to find optimal. It's too expensive. The quantum processor is, and you can see simulated annealing just drops like a solid stone and finds those things. And so the difference here is the problem size. It goes from 175 up to 5,000 variables, and we all know that classical performance will degrade if you give it the same amount of runtime. The horizontal dotted lines are the time limits that were used in our tests. If you give it fixed amount of runtime and ask it to solve a much larger problem, it's going to need more time to investigate each spot as it marches through that landscape looking for a lower ground. And also, the solution space it's looking at is increasing as 2 to the n. It's exponential. And so it's going to slow down and flatten out and have a lower pace of converging to optimal. And that's just a fundamental property of classical computation. And the astonishing thing here is the quantum seems to be going in the opposite direction. You give it bigger problems, and it gets better in the same runtime, which I will say kind of freaked us out a little bit on the benchmarking team. But the fact is, as we thought about it, this is the whole premise of quantum computation, is that it doesn't have bits that can only represent one state at a time, and it's not required to look one solution at a time marching around that space. Because of superposition, and because of entanglement, it's probabilistically representing the whole space in the qubit state, in the quantum superposition state. And it's, help me physicists, it's sensing its ground state and just going there. And that's why, that's what we're seeing is the performance is actually, it's different on the scale, but it's pretty much doing the same thing no matter what you do. And I've been at D-Wave for 10 years, and we've been doing these kinds of tests since the D-Wave 2, and we haven't changed our runtime window of what's interesting. It just doesn't, it's not affected in the same way by N, the important classical thing. The difference is for quantum, it doesn't respond so much to what N is, but it does respond to that embedding and that chain link and how many qubits per chain gets stretched out. And what you see here is that quantum is not so much returning bad answers, it's that the answers it returns are getting degraded when it pops back into the logical space, when it's unembedded. So that's really quite interesting for us. And so for advantage 2, I've got 3 seconds. What's going to happen next is we know that the problems will get bigger, and so the classical solvers are going to move rightward and upward in these spaces. And we know that the system is going to get better in terms of embedding shorter chains, noise suppression, and greater scale. And those blue lines are going to move south. And it may not be enough to catch up with classical and SK, but we do have all of those inputs in that range. And we expect to see more types of inputs tick over to demonstrations of quantum performance advantage in the next system and then the next system and beyond. So I'm done. That's what we're, that's the news from benchmarking, I guess.